In this video, we're going to introduce stoichiometry. Before doing that, I just want to walk through the conversion factors we've introduced as we've talked about chemical reactions. We've been able to show that we can convert between the number of objects we have or things into moles. And for that, we use Avogadro's number. That 1 mole is defined by 6.022 times 10 to the 23rd of these things, usually atoms or molecules. And then the next conversion factor we introduced was the ability to convert between moles of molecule or element and the the mass that it would have. And for that, we used the molar mass that we calculated from the periodic table. And so the units for a molar mass is usually, so using carbon as an example, 12.01 grams per mole. Or you can say 1 mole of carbon equals 12.011 grams. We also looked at mole ratio conversions in 2 ways. We looked at mole ratio conversions within a molecule, and that's really based on the subscripts, although this one is not subscripted, that tell you that in CO2 you've got a mole of carbon atoms and 2 moles of oxygen atoms. And then we also looked at this mole-to-mole ratio, looking at mole ratios between molecules. And these mole ratios are expressed in the coefficients in front of each molecule in a balanced equation. And this allows us to predict the amount of moles that we need to react with something or the amount of product that would form. So in this next lecture that we're going to do about stoichiometry, we're going to utilize 2 of these. We're going to use the mole to mass conversion and the mole to mole conversion between molecules to develop a problem-solving strategy that we call for stoichiometry problems, which is kind of a mouthful of a word. But what we're doing next really just builds on these 2 skills and utilizes them. So stoichiometry is the kind of the big word that we use, but what we really mean is that we want to be able to predict the amount of a product that forms in a chemical reaction. We also can use stoichiometry to, instead of predict the amount of product, but to determine the amount of a reactant that was consumed. This is really the recipe component of chemistry. A lot of what we do is enter the lab and make something by combining different chemicals. It's just the fun part of chemistry, that we can make new things that have never been made before, or we can make something we need from other materials. And in any recipe that you have, it's critical to be able to know the exact amount to combine of your starting materials or your ingredients. As well as predict the amount it will make. And for a recipe, if you're going to make like a batch of cookies, typically you, if you're making up the recipe, you combine your ingredients, and then you just see how much you get, and you write it down, and then you know for the future, I'll get 24 cookies out of this combination of ingredients. And you could report that to someone. You could write it down on a recipe card and hand it off to a friend, and they would be able to make 24 cookies if they combined the same ingredients. And so we typically write out chemical reactions in a way that doesn't specify exact amounts, but rather ratios. And so those ratios give us the tools that we need to determine exactly what mass of my reactants to combine, but they also give us the tools that we need to predict the amount that it will form. So it's a really important way of communicating how to perform a reaction, and an important skill to be able to have in a chemistry lab to interpret a chemical reaction or a chemical equation such that you can perform that reaction and make a specific amount of something that you need. So the way we're going to approach this is using our dimensional analysis tools that we developed in the beginning of the quarter. And we're going to lean on these very heavily. And we're going to present a algorithm for solving a stoichiometry problem. And so the job of the student then becomes recognizing when a problem is a stoichiometry problem, and then being able to effectively apply that algorithm or that problem-solving strategy to get to the answer. So we'll talk through both of these things as we go through this. Whoop, too far. So here's kind of a broad overview of the steps to solve a stoichiometry problem. You'll know you have a stoichiometry problem that needs solving because you'll usually know the chemical equation, and you'll have very little information. You'll usually be only given the amount of one of the reactants or products. And you'll be asked to predict or determine the amount needed or produced of another chemical. So something that's different. So you'll be asked to say the amount that's produced or the amount that reacted of something that you have no information about other than this chemical equation. And that's the big red flag to employ this problem-solving strategy. And what I'm going to show you is how to convert between the mass of one reactant into the expected mass of the product. And then we'll do an example where we go backwards, where we take a known amount of product and we convert into the amount of reactant that was there. So this will start with knowing the mass of the reactant and end at the mass of a product. And to get there, there are 3 steps. We need to convert into moles. We need to then convert into the amount of the product. And then we need to convert into the mass of that product. And so these 3 steps will be the same 3 steps that you use to solve any stoichiometry problem that's asking you to go from mass of one thing to the mass of another. And here are the 5 steps that I typically use to solve. 1, I make sure that the equation is balanced, the chemical equation. 2, I calculate the molar masses of any of my compounds, and this step is really building my conversion factors. Then I'm going to do 3 conversions. It's a 3-step conversion problem. And this is about what we built up to with dimensional analysis, being able to make a strategy for solving something that required 3 conversion steps in a row. So now we're just going to use that skill to use the same pattern of conversions to predict the mass of our product. We'll always convert first from mass to moles. Then we will be able to convert into our desired amount of product. And then we'll go back from moles to mass. And the key here is that this 4th step is that the only way you can convert from one chemical to another is through units of moles. The reason for this is moles is our counting number, right? This is equating a number of molecules that we have in our reaction. And reactions occur with collisions. And so it's these collisions between molecules that produce products. And so we can't work with mass to predict the amount of product that forms because our reactant and our product will have different masses. This conversion from one type of chemical to another is going to come from the mole ratios that we just discussed in our balanced equation, or our recipe for the reaction. So let's walk through one of these. Here is octane, and it will form carbon dioxide and water if it's combusted. This is what your engine is doing in a car. And the way a reaction would be, or sorry, a question would be phrased is, what is the mass of carbon dioxide that forms when 5 grams of octane react? And the key here is that you've been told that you've been given only one piece of information, 5 grams of octane, and you're being asked about the mass of an entirely different molecule. So I want to know about carbon dioxide, but I only have information about octane. Except I do also then have a chemical equation that tells me how octane is converted into carbon dioxide. So those are my red flags that this is a stoichiometry problem. And that means I need to solve this using my 3-step conversion to go from the mass of octane to the mass of carbon dioxide. So step 1 is balance the equation, and that is done for us already. Some of these steps may be done for you in a problem, in which case still go through the number of steps and make sure that it's balanced, but just be like, whew, that's one less thing I have to do. Fantastic. I have 2 molecules of my octane forming 16 molecules of carbon dioxide and 18 of water. So remember, step 2, we're going to build our conversion factors. And so what we're going to need to know is the molar mass of carbon dioxide, and we're going to need to know the molar mass of our octane, and we're going to need to know the mole ratio between carbon dioxide and octane. Those are the 3 conversion factors I'm going to need. First, we're going to need the molar mass of octane for our first step. And then for our second step, we're going to need the mole ratio. And then our molar mass of carbon dioxide will be our third step. So our conversion factor to go between mass and moles will always be a molar mass. For this step, it's in relation to our octane, so I'll use the periodic table to determine the molar mass of octane by multiplying 8 times 12.011 grams per mole. So I have the molar mass of carbon and the number of carbon atoms in my molecule. And I'll add to that 18 times the molar mass of my hydrogen. And that's going to give me molar mass of 114.23 grams per mole. Now, my mole ratio conversion factor is going to be the ratio between my carbon dioxide and octane, which I'm going to get from my coefficients up here in my reaction. So 2 moles of my octane will be equal to 16 moles of my carbon dioxide. So I've built my second conversion factor. Now my third one is the molar mass of carbon dioxide. Again, using the periodic table, I'll calculate this. This time I'll just jump to the answer. It'll be 44.01 grams per mole. And I'd be a little careful with writing out these conversions like this. Remember that when we write it in one line, we really mean 44.01 grams per 1 mole. Sometimes it helps to write these out as equalities. 44.01 grams equals 1 mole. After building conversion factors, then we can actually set up our calculation. So my starting point is my 5 grams of octane, and my endpoint is going to be the mass of carbon dioxide. So I'm going to use that molar mass of octane and use that first to convert into moles of octane. You see these grams are going to cancel out unit-wise. Then I'm going to convert into carbon dioxide, and I have to use the mole ratio to do that, this 2:16. So that's going to come in here. And again, I'm setting this up so that my moles of octane are going to cancel, and I'm left with moles of carbon dioxide. Now, the final step is to convert into mass. And I'm going to use that that conversion factor of my molar mass for carbon dioxide here, setting it up so my moles of carbon dioxide cancel out. So moles of CO2 are on the bottom and grams of CO2 are on the top. And then I plug this into my calculator. I multiply 5 by 16 and 44.01 and divide by 114, 2, and 1. And that gives me 15 grams of carbon dioxide. And that's what these problems will look like. Now we'll go through this again. All right, let's walk through another example problem. In this case, I've been given a combustion reaction for propane, forming carbon dioxide and water when it reacts with oxygen. And I measure the amount of carbon dioxide that's formed. And I find that it's 25.3 grams of carbon dioxide. And I want to know how much oxygen reacted with that propane to form it. So my starting point is now a product, and my end point is a reactant. But our process is exactly the same. And that's kind of the powerful piece of this tool is I can use it to determine any product or reactant as long as I have the mass of one of them. So let's start. First, let's balance our chemical equation. I've got 3 carbon on my reactant side and only 1 on my product, so I'm going to balance that with the 3 coefficient in front of my carbon dioxide. I have 8 hydrogen and only 2 in my product side, so I'll balance that with a 4 coefficient in front of the water. Now I'm going to add up all my oxygen on the product side. I have 3 times 2, that's 6 oxygen from my carbon dioxide. 4 times subscript of 1, that's another 4 oxygen atoms from my water for a total of 10. And I have 2 on my reactant side, so 10 divided by 2 equals 5. Now I have a balanced equation. There's a 1 in front of this propane if it helps to have all of the coefficients out. So next I'm going to build my conversion factors. Especially if I'm feeling a little lost in the problem, I can just build all the conversion factors I could possibly need. One thing I like to do immediately is to write out my mole ratios as one big conversion factor, just as a reminder that that is something I can use. So 1 mole of my propane equals 5 moles of my oxygen, which equals 3 moles of carbon dioxide, and that equals 4 moles of water in this problem. Now I am going to be starting with carbon dioxide and ending at oxygen. So I am going to care a lot about this 5 moles of oxygen and 3 moles of carbon dioxide. That's going to be the equality that I use as a conversion factor in this problem. The other things I'm going to need are the molar mass of oxygen, which is 2 times 15.999 grams per mole, which is going to be equal to 31.998 grams per 1 mole. I could also write this out as an equality. 1 mole of oxygen is going to equal 31.998 grams. I'm also going to need the molar mass of carbon dioxide. So that'll be 12.011 plus 2 times 15.999. That's going to be equal to 44.01 grams per mole. So I have my 3 conversion factors. And remember, this is the tricky thing about this. You won't see conversion factors in the problem like we saw earlier when we learned about dimensional analysis. You have to build them. But now I have the information that I need to actually approach this problem. I know that my starting point is this 25.3 grams of carbon dioxide, and my end point is this mass of oxygen. So 25.3 grams of carbon dioxide is where I'm going to start. And I know stoichiometry problems are always going to be 3 steps, as long as it's mass to mass. And sometimes the problem will do one of these steps for you, and you only have to do 2 steps, which, woohoo! I'm going to end up at mass of oxygen. So no matter what, I'm going to make sure that my last conversion factor has grams of oxygen at the top, and my first conversion factor has grams of carbon dioxide on the bottom. And this way I know that my grams of carbon dioxide are going to cancel out, and I'll be left with units of grams of oxygen, just like we did in our dimensional analysis problems. And so the conversion factors that include mass will always be the molar mass. So the first and last conversion factor will be a molar mass conversion factor. And that first one's going to be carbon dioxide, and the second one will be oxygen. I'll go ahead and put those in, or at least my units. My moles of CO2 will be on top in my first conversion factor, and moles of oxygen will be on the bottom in my last conversion factor. Now, for me to end up with grams of oxygen, I need to be able to cancel out my moles of CO2, and I need to be able to cancel out my moles of oxygen. So to do that, I'll put moles of oxygen on the top of my middle conversion factor and moles of carbon dioxide on the bottom. So now these moles of CO2 will cancel out and moles of oxygen will cancel out. Now that I have this set up, I'm going to go ahead and add in the numeric values to make this actually a calculation I can perform. My molar mass of carbon dioxide we calculated was 44.01 grams in every 1 mole of carbon dioxide. My mole-to-mole ratio we determined was 5 to 3. So that 5 coefficient stays with my oxygen, and the 3 coefficient stays with my CO2. And then the molar mass of my oxygen is 31.998 grams in every 1 mole of O2. Now I have something I can plug into my calculator. If I do this, I'm going to get a value that is 30.7 grams of oxygen, and that's my answer. That's my prediction for the amount of oxygen that reacted with my propane. And here is, in your slides, the typed out version of each step individually rather than all together in 3 steps in one. And so if it's easier to break this down into 3 individual steps, please do. For stoichiometry problems, I think the best advice is to build a pattern that allows you to replicate this algorithm every time you recognize a stoichiometry problem. Another piece of information that's important to communicate is your percent yield. So stoichiometry problems allow us to determine the theoretical yield of a reaction. So when we predict the amount of products, we're predicting the amount that will form if everything goes right, if every molecule of a starting material becomes a product. Lots of things go a little bit differently in lab. We sometimes weigh slightly different amounts than we were supposed to, or spill a drop, or sometimes we have side reactions that occur that prevent 100% conversion, or our reactions will be in an equilibrium that will prevent it as well. So it's when we report a recipe, we actually in chemistry also present percentage yield. It's kind of like if you were reading a cookie recipe, if after it said produces 24 cookies, it said with a percent yield of 50%, which means This recipe, if you follow it, is likely to produce half of the cookies that are not edible. Maybe the temperature that is communicated is incorrect. This isn't something we see in our daily life, but it's really helpful as a way to check if the reaction went well or not in chemistry. So we calculate the theoretical yield using stoichiometry, and we compare it to the actual yield that we measure in lab. So the actual yield is what we measure when we do the experiment. And so our percent yield is a ratio of these two, that actual amount we made divided by what we hoped we would make times 100. Be careful with this percentage. We're multiplying it by 100 to be able to report a percentage. Do not use the percent button on your calculator. A lot of times that actually will convert this into a fraction in the incorrect way. It's just an odd button on some calculators, not all. So let's try one of these. So following up the problem we did, we determined that, or when we were looking at propane being converted into water. So if we had 15 grams of carbon dioxide that would be produced, theoretically, from a reaction between 5 grams of propane and lots of oxygen. But at the end of the day, we only collect 12.4 grams of carbon dioxide. What is the percent yield? So part of this is which number are we using from our stoichiometry problem? It's going to correlate with the product, the 15.0 grams. So my percent yield will be equal to what I actually measure over what I theoretically could make times 100. So what I actually measured was 12.4 grams of carbon dioxide. What I hoped to make was 15.0 grams. That's what I predicted from a stoichiometry problem. So I'll take those two and divide them to get the percent yield. And if I plug that into my calculator, I'm going to get a value that is 82.7% yield, which is a really good yield for a chemistry experiment. So these won't have units because they canceled out. We'll just report the percentage. All right, here is another stoichiometry problem. And it tries to walk you through the different steps, the determining your conversion factors, converting to moles of desired product and back to mass, and putting it all together. And so try this on your own, and in a later video I will walk through a detailed solution.